we'll kick on. For those of you that didn't do the aerodynamics, that haven't met me before, my name's Jim Campbell, and I am going to be teaching module 11 to you guys. As I was saying earlier, it's a fairly big module, but because you're in the aviation industry, you should have a good idea of what's going on. So don't be scared by the amount of material. You'll come to realise how much you actually know as we go through the various subjects.
Power off.
From day one, that's today, we're going to break down the subjects into days. Some days will be long, some days will be short. Just depends on the subject. So we'll take our time, we'll go through it. If I see things I recognise that have come up previously, I'll obviously let you know. But it's all fairly simple, fairly straightforward stuff. The program that we're going to look at, we're going to do day one today is going to be basic structures, very basic. Pardon me. Tomorrow we'll look at book 2, air conditioning. Wednesday, book 3, part 1, which is ice protection. Day 4, book 4, fuel systems. Book 5, hydraulics. Then we have the weekend. The following week we'll finish off the hydraulics and we'll do pneumatics. Pneumatics is a very short subject, so we'll finish hydraulics, do pneumatics. Then we'll have a look at fire protection, which is book 3, part 2. Because fire protection is a very short module, we can get that covered in the morning. So on day 7, we'll look at fire protection. We'll spend the morning doing that. And then in the afternoon, another very short subject is water and waste on the aeroplane. Day 8, we'll have a look at pressurization and oxygen systems. Day 9, the theory of flight. The theory of flight is different to aerodynamics, although the two of them do cross over a bit. But we look at the mechanics, the theory behind flight, and then we go on to flying controls. And flying controls is actually how we put that theory into practice. I've just got a couple more want to come in. Yeah, once we've finished flying controls, we'll have a look at landing gear. Again, landing gear is a big book, but although there's a lot of content there, it's nothing to be scared of, nothing to worry about. And with landing gear, there's a lot of pictures, which makes the book a lot bigger. Yep. Once we've finished landing gear, we'll have a look at structures and furnishings. And then on the last day, we'll go through everything that we've covered. Yeah. I have got open questions that I can send out. So what I need is a class leader, somebody who's going to be the go-between between me and the rest of the class. And what I'll do is I'll email questions to the class leader, and he can hand them out to everybody else. So, any volunteers? Is that you putting your hand up, Yadav?
Yeah, I can, sir.
So, Yadav, you're going to be the. Would you send me a quick email just so I can get your email address?
Surendai.
Did you get that, Yadav?
Yeah, I will send you the email.
Thank you very much. You've got my email address, haven't you?
Yes.
Excellent. And then what I'll do when we've got questions, I'll send them to you. You can print them off, photocopy them, and hand them out. And it'll just make life a lot easier. Getting lots of people joining us, which is nice. Right, so that was the layout. Yeah, so start today, structures, conditioning tomorrow, protection, fuel, and hydraulics, and that is the subjects for this week. What else have we got to say? The day you guys have been working with Scott before the holidays, and I'm going to follow the same sort of pattern as Scott. We'll have a couple of morning breaks. I know you guys like to wander over the road and get your coffee and your momos and all the rest of it. So we'll have a couple of breaks during the morning and a couple of breaks in the afternoon, 20 minutes, just to get a stretch, get away from the computer screen, just get our thoughts together. So we'll have those break times. We'll have an hour for lunch, same as we did before with Scott. Can't really think of anything else to tell you. For the guys that haven't met me, I'm Jim. I was in the Air Force for 30 years as a mechanical engineer. I left the Air Force and I've been with AST for 12 years now. I've been lucky enough to come to Nepal a couple of times, so some of you will have met me or possibly heard about me. What I would say is, because this is long distance, because it's a bit awkward, if you're not understanding, if the line's not very clear, if you need me to go over anything, say so. Don't be shy. Don't be worried about looking silly. Ask questions. Don't be afraid to interrupt me if you don't understand what I've been saying. If I'm speaking too quickly, tell me. Right, so now, hopefully, everybody on the screen should see the title slide for basic aircraft structures. Can everybody see that okay?
Yeah, that's okay.
Okay, sir. It's clear.
Okay.
Brilliant.
Yeah.
Harry, yes. Harry, you got your hand up?
Yes, I got, sir.
Oh, good, good. Right, let's see. All I can see on the screen is people putting their hands up, so... That's good. Right, so basic aircraft structures then.
सुरेन्द्र दाइ,
Yes.
म्युट गर्नु नि, तपाईँको आवाज नोइज आउँछ क्या?
किन?
नोइज आउँछ हामीलाई. त्यो आवाज नोइज आउँछ क्या?
Can everybody see okay?
म्युट
Please, everybody
गरेर
mute their mic.
नोइज आउँछ.
Please, everybody mute their mic.
Apart from me.
From you, sir, yeah.
Yeah. Right, everybody mute. Everybody can see. I can see all the hands up. That's fantastic. Fantastic. Right, where have we gone? Right, I'm just trying to find me a slide for myself. That's lovely. Excellent. Right, aircraft, basic aircraft structures then. You guys work on aircraft. You should be more than familiar with all the terminology. But what we need to do, we all need to speak the same aviation language. Yeah, so to make sure we're all singing off the same song sheet, somebody else coming in. Yeah, just so we're all talking the same thing. The aircraft itself, the names of the various components. Obviously, we've got the fuselage. The fuselage is where we're going to keep the cargo, going to keep the passengers, and a lot of the equipment. Stuck on the sides of the fuselage, we have the wings. Now, sometimes we'll hear the wings being referred to as main planes. So if you hear the expression main plane, it is a wing. On the wings, we've got the flying controls, the basic flying controls, the leading edge flaps, trailing edge flaps, and that's going to give us our high lift. We've got the ailerons that are going to give us roll control, and bolted onto the wings, some, depending on your aircraft type, you've got the engines. Yeah, the engines contained in nacelles. The nacelles are just the surrounding structure for the engines, and the engines held onto the wings by pylons. I know we're talking generic. I know there's all different types of aeroplanes. I think you guys work on the jet stream. Sorry, I keep getting people wanting to join. I've got all these people wanting to join us. Stop people dropping out. Yeah, the back end of the aeroplane is collectively known as the empennage. The empennage, a French word, yeah, and it's just the collective name for the whole of the rear of the aircraft. Within the empennage, we've got the fin, or the vertical stabilizer. On the back of the vertical stabilizer, we've got the rudder. And the rudder giving us our yaw, or directional control. We've got the horizontal stabilizers, or the tailplane. And again, on the back of the tailplane, we've got the elevators. And the elevators are there to give us our pitch control. So all of that little lot, the empennage. The terminology, yeah, we're just making sure that we're all using the same expressions. So when we're talking about areas on the aircraft, components on the aircraft, everybody knows what we're talking about. When we design an aircraft, we want to design and produce an aircraft. And lots of people joining us today. Yeah, when we design an aircraft, we want to make sure that that aircraft is going to be safe to operate. So it needs to meet certain criteria to make sure that it's going to be airworthy. Those criteria are set out in what they call certification specifications. Now, EASA, we're doing the EASA regulations, the EASA specifications, and EASA, when we come to design and build an aircraft, they will put certain specifications that we have to meet. And those specifications are laid out in CS23 and CS-25 for fixed-wing aeroplanes, and CS-27, CS-29 for rotorcraft, rotary wing aeroplanes. So your CS-23, yeah, for your normal utility, little commuter aircraft. Your CS-25 is for the big boys, the large aircraft. 27, small helicopters, and 29 for the large helicopters. And those certification specifications are worth remembering, yeah, because they're going to tell us all the details, the criteria we need to meet for the aircraft that we're designing. Yeah. Part of those design specifications is that the aircraft is, no matter whereabouts in the world we're going to operate, it's going to be operating within the environment, within weather. Yeah, and that weather is going to create turbulence, and that turbulence is going to create updrafts. It's going to cause the aircraft to move in the sky. So we need to make sure that the structure of the aeroplane is going to be strong enough to withstand the forces that it's going to be subject to during its normal operations. Just 1 second. Yeah. Yeah, our aircraft, we're going to fly it. It's going to go up into the sky. All the turbulence and weather and all the rest of it up in the sky is going to bounce the aircraft bounce the aircraft around. So what we need to do is to make sure that the aircraft is strong enough and capable of withstanding those loads, and those loads are expressed in terms of G. Yeah, so when we talk about G on an aircraft, what we're doing is we are comparing the weight of the aircraft to the pull of gravity. Yeah. When an aircraft's flying, yeah, the four forces of flight, yeah, when the aircraft's airborne, it's got a constant speed, constant altitude. The lift being produced by the aircraft is equal to the aircraft's weight, and that's termed as 1G. Sorry, I'm flitting backwards and forwards because there's people keep. I don't know whether the signals are dropping out, but we get people waiting in the lobby, so it says. Yeah, where did we get to? Yeah, so G denotes the acceleration caused by the force of gravity. So if we straight and level, no interference on the aircraft is subject to a load of 1G. Yeah, same as when the aircraft's parked on the ground. When its wheels are on the ground, the force of gravity pulling it down equal to the weight. That's a 1G loading on the aircraft. Newton's law, yeah, a body will continue in its path, selected path, unless there is an outside force applied to change its direction. So if we change the velocity of the aircraft, yeah, there's going to be positive or negative acceleration forces applied to the aircraft. If we maneuver the aircraft, we're putting an accelerative force onto the aircraft to overcome the pull of gravity. So that the amount of accelerative force that we're applying to overcome that gravity is going to be expressed in terms of G. Yeah. that maneuvering is known as the load factor. That's expressed in terms of G. G, the ratio of the forces experienced during the acceleration compared to the forces existing at normal 1G state. So we're flying along straight, level, constant speed, constant altitude. We're subject to a force of 1G. The lift and the weight of the aircraft is balanced. If I need to change direction of the aircraft, obviously I've got to create lift on one part. Creating that lift is going to put a force on the aeroplane, and that force again is expressed in terms of G. All right. Where are we going with this? Yeah. So flying along straight and level. Yeah, we're nice lift weight balance. This is getting a bit silly now. Right, hopefully that is it. Does it, Yadav, have you got any idea how many people are meant to be on the course?
No idea, sir.
No idea. That's all right. I'll speak to Sanjeev. I just thought you might know offhand. Because nobody told me. Nobody wanted to speak to me.
Yeah, they could have better. It will be better if they send you the email with the student name.
Yes, yeah, I'll get him to do that. I'll speak to him shortly when we have a cup of tea. Anyhow, we're flying along straight and level. Yeah, there's no force on the aircraft. We've just got a 1G pull. As I now maneuver the aircraft, yeah, I've got to put an accelerative force on. I'm creating lift, which is going to maneuver the aircraft. And the more lift I'm creating, I've got to overcome the weight of the aircraft, so that the more lift I create, the more G that I am going to pull. And that load factor, the steeper that we bank the aircraft, the more that G loading is going to increase. The more the G loading increases, the more stress we're putting on the structure of the aircraft. So we need to be very careful in our design, the materials that we use, to make sure that the aircraft is going to be capable of withstanding the force and the loads that we're applying to it. So that the aircraft is limited to the amount of maneuvering it can carry out. Yeah. Likewise, the aircraft is limited to the amount of weight that it can carry. The heavier the aeroplane, the more load we need to maneuver the aeroplane. And if that aircraft's too heavy, the force that we need to overcome the weight, yeah, again, that could create structural damage. So one of the ways we can get around that is to limit the amount of weight that the aircraft can take off with. So we have what they call the maximum takeoff mass, or the MTOM of the aircraft. And that maximum takeoff mass is there to ensure that we don't over-maneuver the aircraft, and we don't overstress the aircraft, and we don't damage the aircraft while we're in flight. Everybody okay with that? Anybody got any questions there? No? Okay.
No.
Sound. All right. So we've designing our aircraft, and with certification specifications state that the aircraft has got to be strong enough to withstand the normal gusts and loads that we'd experience during normal flight. So the materials that we use have got to be capable of withstanding those loads, and the amount of manoeuvring we do on the aircraft has got to be limited so we don't overstress it, we don't damage it. So we're going to put limits on the amount of manoeuvring we can do on the aeroplane. Yeah, the amount of load that we're going to subject the aircraft to. And there are two loads. There is the limit load, and the limit load is the maximum load that we would expect under normal in-service operations. So if I was designing my aeroplane and I am going to operate in Nepal, for example, yeah, around the mountains, we'll go sightseeing down to Everest. That's one of the common routes for you guys. I'd expect quite a lot of turbulence in the mountains. Yeah, a lot of bouncing up and down for the aircraft. So when I'm designing it, I want the aircraft to be strong enough to withstand those loads. They're just going to be the normal that I'd expect, and I don't want the aircraft damaged by them. However, because it's aviation, there is going to be occasions where we're going to exceed those limit loads, the maximum that we'd expect in service. So to cater for that, to compensate for that, we build the aircraft with a safety factor built in. And that safety factor is known as the ultimate load. Yeah. The ultimate load is 1.5 times the limit load. So if I've got a limit load of, let's say, 5G, 5G is the maximum loading I'm expecting during normal operations. What would be the ultimate load on the aeroplane?
Half of that.
Yeah, so it'd be 5G plus
7.5.
7.5. That's it exactly. Yeah. So now we've got that built-in safety margin, and that built-in safety margin is our ultimate load. With the limit load, yeah, if we go up to the limit load, there should be no damage to the aeroplane. Maybe a little bit of minor deformation. Nothing too dramatic. If we go over the limit load up to the ultimate load, there will be some sort of damage, but nothing structurally significant. If we go over the ultimate load, then we are going to have severe damage and possible failure of the aircraft structure. So we should never ever exceed the limit load under normal operations. If we do, we've got that ultimate load. If we exceed the ultimate load, then there is the possibility of the aircraft falling apart. Yeah. So what we've got to do is to prove that the aircraft is going to be strong enough to withstand those loads. So part of the design and the certification specifications tell us that we've got to withstand those loads. Part of the design and the build of the aircraft is to prove that the aircraft is strong enough. And we'll come on to that in a minute. When we're talking about the structural loads, the loads that are on the aircraft, we've got stress and we've got strain. The stress is the amount of load that we're applying, and the strain is the amount of deformation that is caused by that. Just let somebody else in. Okay. Right, so our limit load then. obviously, depending on the aircraft that we're designing, what we're going to do with it. If I've got a, well, I don't know, let's say 737, that's going to be just journeying passengers, pretty much straight line from A to B. We're not going to subject the aircraft to too much extraordinary load, just the normal environmental conditions that we experience. If I've got a little aerobatic aeroplane, yeah, that little aerobatic aeroplane is going to be subject to a lot more loading, so the structure has got to be a lot stronger, I should say. Yep. So the limit load, the maximum loads expected for that particular aeroplane in service. The ultimate load, yeah, is the limit load multiplied by that safety factor, and that safety factor, as we said a minute ago, is normally 1.5 times the limit load. That gives you your ultimate load. Yeah. The slide on the screen, that was actually a C-130 that the Americans used for firefighting. You can actually see a video of it on YouTube. And he went away to do his water bombing, came over the fire, and all of a sudden the main spars on the wings just collapsed, gave way. When they were doing the investigation afterwards, they reckon that because the aircraft was holding all this water, the weight that the aircraft was carrying was way outside the design limits for the aeroplane, and because the aircraft was aging, because it had been kicking on a bit, we ended up with this structural failure. So like I say, if you're interested, there is a clip of that on YouTube. Yeah, so that's our limit load. Yeah, I need to make sure that the structure is strong enough to withstand the loads that it's going to be subject to during normal operation. And again, we can see there failure of the structure at the wingtip. So how are we going to convince the authority that the aircraft is good enough and strong enough to withstand those loads? We're going to do it by demonstration. Yeah, there are various ways we can demonstrate the strength of the aeroplane. We can use test rigs, and we can demonstrate by static testing that the structure is going to be strong enough to hold those loads. This one, the jig, what they do, they'll take an aircraft from the production line, and they'll stick it into a jig where they will test the structure pretty much to destruction. And in this case, I don't know whether you can see there, they were doing the strength check on the wings. And what they do, they put strain gauges all over the wings, and then they flex the wings. They see how much load those wings are going to be taking. Yeah, and they apply more and more and more load until we eventually get to the point of failure. Yeah. The other way they check the ultimate load to make sure that the structure is strong enough is they will take the aircraft up to the ultimate load, and it's got to be able to cope with that load for 3 seconds. Yeah. If you think about it, we're pulling G, and if we're in a situation where we've got to pull excess G loading for more than 3 seconds, we're in a whole world of pain anyway. Yeah. So that 3 seconds, yeah. Let's just say we're flying along in the mountains, and all of a sudden there's a little helicopter in front of us. We've got to pull back on the stick. Yeah, we could well go over the limit load up to the ultimate load, and so long as we can hold that without any damage for 3 seconds, we're okay. If it takes us any more than 3 seconds to avoid the helicopter, then we shouldn't be flying, really. Yeah, so that's how we're going to check and prove the structure. Everybody okay with that? Yeah. Right. The loads that we're going to subject the aircraft to. We talked about the structural loading. We've got stress and we've got strain. Stress is the amount of load that's being applied, and strain is the amount of deformity that stress causes. The ability of the material to return to its original condition is known as its elasticity, its elastic properties. Yeah, so I'll apply a load on the aircraft. We'll get that deformation, that strain. As I remove the load, if the structure goes back to its original shape, that is its elasticity. And again, those terms were worth remembering. Stress, the amount of load that we apply. Strain, the amount of deformation that's caused by that stress. And elasticity, the ability of the material to return to its original condition. If we go past the point of the elastic limit, then we are going to get permanent deformation of the structure. Yeah, permanent twisting, warping, whatever it might be, and that's where you get oil canning on wings. Yeah, where the structure is flexing. Ta-da! Right. Our aircraft structure, yeah, the various components on the aircraft, we categorize into primary and secondary structure. Primary structure, if that primary structure failed, it could lead to catastrophic loss of the aeroplane. In other words, the aircraft is going to break up and fall out of the sky. Something like a wing spar would be primary structure, because if that wing spar failed, there's a good chance the wing's going to fall off, and that's going to spoil your day. If we had failure of a power control unit due to failure of a piece of structure, so let's say aileron actuator, the attachment bracket for that actuator would be classed as primary structure, because if that bracket failed, the power unit wouldn't operate. Yeah. Any piece of structure where its failure, if it failed, it would lead to injury to the occupants of the aircraft. So something like your seat structure. Yeah, if the seat structure failed, if the seat collapsed, you're likely to hurt yourself. Now, it doesn't specify it's got to be a severe injury. Yeah, if the seat failed, you might break your ankle. You're not going to die from a broken ankle, but because that seat failed, it caused you injury, so it would be classified as primary structure. And the other way we classify primary structure is if there was a failure of that, it would lead to uncommanded movement of the aircraft, or loss of operation of control of the aircraft. So again, let's say a hinge for a spoiler. Yeah, if that hinge failed, the spoiler could start moving, and that will give us uncommanded movement of the aircraft, something that the pilot hasn't requested. So that spoiler bracket, spoiler hinge, would be classed as primary structure. Pardon me. On top of that, we've got secondary structure. Secondary structure is where that structure is so strong, yeah, for the job it's doing, there is little risk of failure. So it's got a big reserve of strength in it. Some stringers classified as secondary structure because they're strong enough to cope. There'll be a lot of load applied to it, and they're very unlikely to fail, just from the material they're made out of or where they're positioned. So that's our secondary structure. The other type of structure we get is what they call tertiary. And tertiary is niff-naff. It's decorative. It carries no structural loading whatsoever. Tertiary is falling out of use as terminology now. People don't talk about tertiary structure very often. But just be aware, if anybody is talking about it, that's what it means. You'll notice on the slide that primary structure is coloured red and secondary structure is coloured yellow. And that's because a lot of manufacturers now, when they're producing the structural repair manual, the SRM, to make it easier to identify the type of structure we've got, the illustrations in the manuals are coloured. And if you see a piece of structure that's coloured red, you'll know it's primary structure. If you see a piece that's coloured yellow, you'll know it's secondary structure. Yeah. The other thing we have are what they call PSEs. Some bits more important than others. Yeah, so a principal structural element, or a PSE, is any component that contributes significantly to carrying flight, ground, and pressurization loads. Yeah, so your pressurization loads, obviously the aircraft pressurizing, depressurizing, inflating, deflating constantly. Yeah, and something that's taken, a component that's taking those loads would be classified as a PSE. Something like a landing gear attachment bracket, yeah, that would be a principal structural element because it's carrying heavy ground loads, and the failure of that could be quite painful, quite catastrophic. Yeah, just idea of some of the damage that can occur. Yeah, you're looking at your cracking emanating from your fastener holes. And again, that was a landing gear bearing that they found cracked. All right. Has anybody got any questions on any of that we've covered there?
Yes, sir, I have got the question, sir.
You've got a question. Who's that? That's
Yes,
Krishna. Yes.
Sir, you told the spoiler hinge is the primary structure, but spoiler is the secondary, no, sir?
No, the aircraft is divided into primary structure and secondary structure.
Yeah.
The primary structure, just let me kick back. Primary structure is classified if a piece of structure failed and that caused catastrophic failure of the aircraft, i.e. the wings dropping off or the fin dropping off, yeah.
Yes.
The attachment bracket would be classed as primary structure because failure of that would lead to catastrophic failure. Okay. If a piece of structure failed and it led to power unit failure, yeah, again, that structure attaching that is classed as primary structure. Any piece of structure, if it failed, that could cause injury to occupants, again, would be classified as primary. And when we talk about uncommanded operation or loss of operation, uncommanded means an input, a manoeuvring of the aircraft that's not requested by the pilot or the autopilot. Yeah, so if, well, I used the spoiler as an example. If I had or should we try an experiment?
Okay, sir.
Yeah. You say that all right? If that's my wing, and on top of the wing I've got my spoiler, and the spoiler normally lies flush with the upper surface. And that spoiler's got a hinge. Yeah. If that hinge bracket failed, there'd be nothing to stop that spoiler moving, and that spoiler could start to raise in flight. Yeah. If that spoiler raised in flight, it's going to cause an uncommanded movement of the aeroplane. So that the hinge that we're talking about would be classified as primary structure, because if it failed, it would lead to uncommanded operation, or indeed loss of operation. Your secondary structure, yeah, is structure that's strong. It's very, very unlikely to fail. Yeah. I forgot where I was going with that. Yeah. Yeah, right. Sorry. Primary structure. If it fails, there's going to be some serious damage. Secondary structure has got that much strength built into it. It's very unlikely to fail. Has that answered your question?
Thank you, sir.
Is that okay, Sanjay? That answered
Yes,
your
sir.
question?
I'm okay, sir. Yeah.
Okay. Anybody else got any questions there?
Sir, I have one question, sir.
Yep.
Can you please explain the reserve of strength, sir, of secondary structure?
Yeah. Where's me? Yes, I can. Just let me go back to secondary structure. If I'm building a piece of structure, yeah, and I make it out of, how can I? Trying to think of an example. Piece of structure, because it's so strong, it's very, very unlikely to fail. Yeah. If it fails, it's not going to create any of the problems that you get with your primary structure. It's not going to lead to catastrophic failure, not going to lead to injury, anything like that. It's going to be very, very unlikely to fail because it's got so much strength built into it. Just try to think of an example on the aircraft. What type of aircraft do you work on?
Dornier 228, sir.
Sorry?
Dornier 228.
Dornier 228, okay. So on your Dornier 228, where you've got the seats, the seats are attached to seat rails, yeah? So the seats are attached to the aircraft's longerons. Is that right?
Yes, sir.
Okay. So where those seats attached to the longerons, if that longeron failed, it would cause injury to you. Yeah. So that would be classified as primary structure.
Primary structure, okay.
The floor around that, yeah, is very, very strong, and the floor is very unlikely to fail because it's got inbuilt strength into it. Yeah, so the flooring would be classified as secondary structure. There's so much strength in there, it's very, very unlikely to fail. So, do you see what I mean?
Yes, sir. Thank you, sir. I've got my answer.
Okay, that's good then. Yeah, we won't worry about tertiary. Tertiary is just like trim. There's no structural strength attached to it whatsoever. Right, I think what we'll do there, that's nearly 10 past 10. Nearly 10:10. So I think what we'll do there, we'll have a cup of tea, yeah? Everybody okay with that?
Okay, sir. How long, sir? 10 minutes?
No, we'll go from, well, I make it 10:07 now, so we'll say 20 minutes, we'll say 10:30. So if everybody could be back for 10:30.
Okay, sir.
Please.
Okay.
And that tea plantation's in Nepal as well. I looked it up specially.
Yes, sir.
Okay, 10:30, please.
Okay, sir. Thank you.
Copy 10:30, sir.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Okay.